Hello and welcome back to this course. So, in the last class we looked at inexact and exact differentials. So, we are now going to go on to the next concept, which is that of work. The word is quite familiar with us. We have looked at this in mechanics, where for example we define work as the force into the displacement in the direction of the force. Mathematically that would be the integral of f ds, where ds is a small displacement and f is the force, and we can find out the work in that way. In thermodynamics, our way of looking at work is slightly different, but before that, of course, we also know that power is the rate of doing work, which is a definition which we are going to use in both mechanics and in thermodynamics. But for work itself, our definition in thermodynamics deals with energy. So, we look at work as an energy interaction between the system and the surroundings. So, we defined the system earlier as the mass which we are interested in, and the surroundings as anything else which is external to the system. So, we are going to look at work as an energy interaction. Of course, we have not yet defined what energy is. We have some idea of it from earlier. We will sort of formally define it when we go on to the first law, and it may seem sort of like a chicken and egg thing, where we define energy in terms of work and work in terms of energy, but we will stick with that for the time being and then see what we can do with it. So, we have a sort of little more complicated definition of work, but it is not all that complicated once we look into it. So, we say that work is said to be done by a system during a given operation if the sole effect external to the system could be reduced to the raising of a weight through a distance. So, we will look at all of these things. So, work is said to be done by a system, which is okay. So, which means the work is done by a system on its surroundings during a given operation if the sole effect. So, sole effect means one and only effect. So, it means that if the effect of the system is only one effect, and that effect which is external to the system, which means that we are not going to look at anything which happens inside the system when this process happens. We are only interested in what happens outside the system. So, that is what we mean by external to the system. So, this sort of emphasizes that work is interaction between the system and the surroundings. So, we say work is done in the system if the sole effect external to the system, and then we say could be reduced to raising of a weight. So, it means that there does not actually have to be a weight which is raised, but if whatever is being done by the system on its surroundings can be thought of as raising a weight, then in that case we say that work is done. Okay. So, that is essentially what we mean by work. So, you might want to pause here and go through the definition again and try to see if you have understood it before going ahead. But what we are going to do now is to look at some examples. So, I have here at least two systems which are marked by these dotted lines. So, one is a battery, a second is this gas surrounding a paddle wheel which is confined inside a box of some kind. I can also think of a third system which is essentially this motor over here. So, I have this battery, it is connected to a motor, this motor is connected to a paddle wheel, and the paddle wheel is rotating inside a gas. So, let us say I switch on this circuit, then there is energy flow from this battery makes the motor run. When this motor runs, the shaft spins, this fan over here rotates, and the gas inside this system is rotated. So, this definitely does not look like there is any weight or any work which is done, but what I could do, supposing instead of this fan I had a weight. So, I have this motor, I have this shaft. So, instead of a fan, if for example I had a long string which is wound against this, and I had a weight. So, when this motor spins, the action of this motor, which is now being used to circulate this air, could be used to raise this weight. So, as it spins, this is going to wind, the thread is going to wind around the motor shaft and the weight is going to be lifted. So, in this case we could think of this as work being done on this gas by this battery. Of course, in between there are other things. What we are assuming is that this motor is an ideal motor. There is no such thing, but in thermodynamics we make some assumptions as to the ideality of substances. So, we assume this is an ideal motor, which means it does not have any losses. We assume that the shaft and fan, everything is ideal, the battery is ideal, and so on. Many of those assumptions we will see are not bad at all for a first cut answer for the problems which we want to solve. So, in this case what we would say is the battery which is connected to this shaft, which is connected to this fan, all of this is essentially doing work on this gas, because it is as if there was a weight inside over here. For this system, this weight is external to this battery system, and we would be lifting up this weight. So, in that case we would say work is being done. We have a sign convention with respect to work. We will see that not everybody agrees on the sign convention. Some books use different sign conventions. If you look at books in chemistry, for example, they use slightly different conventions, but more or less all the mechanical engineering books you will find they use the same convention. So, we say that the work done is positive if it is done by the system on its surroundings. So, work done by system we consider as positive, and work done on the system we consider as negative. So, more commonly what we would refer to is work interaction for the system. Instead of saying it is done by the system or on the system, we would say work, sorry about that. We would say work interaction for the system, and depending on whether it is positive or negative, we know whether work is done on the system or by the system on its surroundings. So, this is the convention which we are going to follow in the rest of this course. There are various forms of work. One of them is what is called as displacement work, and this is sort of the most common example we use in this course because it is sort of easy to visualize. So, this is the work involved when a system boundary sweeps a volume when interacting with its surroundings, and the easiest way to sort of think of this is where we have some kind of a piston cylinder arrangement. So, we have a cylinder, we have a piston. This piston is free to move. It seals the cylinder, but it is frictionless, and the piston can move up or down. So, when this piston moves, the volume of this control volume, which is here, increases or decreases, and as this piston moves, it sweeps a volume which may be against the surroundings or against the system. So, if this piston is moving upwards, then the volume of the control volume or system which we have here is increasing, and then we would say that this volume is swept against the surroundings and the work done is positive. So, the system increases its volume at the cost of its surroundings. So, it is positive for the system and negative for the surroundings. And if this piston was to move downwards, it reduces the volume of the system, and then we would consider that work to be negative. And we say that this can be evaluated only for a quasi-static process. We will look at in a minute what this term is. It is a fairly important term. We will keep using this all over the place. So, we will define it, and we are generally considering this kind of displacement work to be a system containing a gas or a liquid or something like that, where we are assuming that magnetic and usually gravity and electric forces are not important. We generally neglect magnetic and electric fields because for the kind of systems we are going to deal with in this course, they are not important. Gravitational field could be important in a few cases, but in many cases we see that that also is not something we need to take into account. So, we still need to look at what is this quasi-static process, and we will try to see that. So, we said earlier that work is done when you have interaction between the system and the surroundings, and then we said the sole effect external to the system should be reducible to lifting of a weight. So, let us say I have a system of this kind. So, my system here is gas inside a piston cylinder arrangement. We have all seen piston cylinder arrangements. Of course, a common example of a piston cylinder would be one of these. If you take a plastic medical syringe, you close one end of it and you try to push the plunger in. Many of us might have played with this kind of thing. So, that is a piston cylinder arrangement. Of course, what we have here is a more sophisticated piston cylinder, and in that kind of a piston cylinder which we have played it, we find that there is a lot of friction. It is very hard to move the plunger in or out, but here let us say we have an ideal piston cylinder arrangement. So, we have the cylinder here, we have the piston, we are assuming that the piston is frictionless, so it can easily move. What we are also going to assume is that this piston is massless. Of course, there is no such thing as a massless piston, but let us say the mass of the piston was extremely small compared to whatever else we are going to deal with. So, we can neglect it. So, that would be a massless frictionless piston, an ideal piston cylinder arrangement, which is what we are generally going to look at in the rest of this course. So, let us say there was a big block sitting on it. It has this block has some mass and it is sitting on this piston cylinder arrangement. So, the pressure inside must be high because this block is sitting on it and this is in equilibrium, it is not moving, it is stationary. So, the pressure inside must be high. If I suddenly remove this block from the top of this piston arrangement, so what we would expect is outside the pressure is atmospheric, inside the pressure here was some P which was high, it is higher than the atmospheric pressure. This piston does not have any mass, it does not have any friction, so it is free to move. So, this piston would move until the pressure inside became atmospheric. So, the gases inside would expand, the piston would move up. We are assuming that the cylinder is tall enough that the piston would not jump out, the piston can move up and the volume of the system will expand and the pressure inside would become atmospheric. Now, if we suddenly remove this block and then this piston is moving, the thing is that we see that there is expansion of the system, but the question is what is the mass which was or the weight which was raised. Okay. For a first cut approximation, what I am going to say is I am going to ignore all the outside air also. So, if this experiment was for example done in vacuum, there was no air outside. So, let us say the pressure outside was also not there, okay, or even if it is there, it is, let us say it is very small compared to the pressure inside. So, what we see is if I suddenly remove this block, this piston moves up. So, there is displacement of the boundary of this system, but there is no raising of a weight because there is no weight to raise. So, since we said work is done only if whatever happens is equivalent to the raising of a weight and there was no weight which was raised, so the work done here must be close to 0, ignoring the atmospheric pressure around. So, what we see is that if we have a block like this and suddenly remove it and there is expansion, we do not really get much work at all. So, what I can now do is do a slightly different experiment. I cut this block into two. Sorry about that. So, let us say I cut this block into two. I now have both two blocks. The sum of the masses of both the blocks is what was there earlier, and I remove the top block. So, once I do that, I have one block here and this piston is going to move. I suddenly remove it. I have just suddenly removed the top block. Now, this is going to move up. This piston is going to move up here and expand. The pressure was higher in this, it was the same as what it was in the previous case initially because the same mass was sitting on top, the same amount of gas and so on. And now I have removed one block. It is going to move up to a certain extent till the pressure inside is balanced by the mass of this block and atmospheric pressure, and then it is going to stop. So, in this case what I see is I get some work because I have this block which has a mass of m by 2 if the original mass was m, and that m by 2 mass has been displaced by a certain distance. So, now I get some amount of work which is done because I have the raising of a mass by the gases inside this piston cylinder arrangement. So, what we see is if we had this entire thing as one block and removed it, we did not get much work. If I can now cut it into half and remove half, I got some amount of work. So, the train of thought is that if this is going to help, then why not cut this into more number of pieces. For example, I can cut it into 4 pieces, remove one piece, it will move to a certain extent, then it will raise 3 blocks. I have 4 pieces. So, if I had cut this into 4, if I remove this first piece, this piston would move up moving these 3 pieces, then I remove the second piece, piston would move up with 2 pieces, then I remove the third piece, it would move up, and then I have the 4th piece. So, I will get more work in this fashion than if I remove the entire block. And in the limit of this, what I could think of is that I cut it into a large number of extremely small pieces. Actually, even larger number of this, each of them can be as small as a grain of sand. I remove one small piece at a time. So, each time I remove a small piece, the piston moves up a negligibly small amount, and then I remove one more piece, the piston moves up slightly more. But each time when it is moving up, it is lifting so many other pieces. So, it is lifting a larger mass. So, I am getting work because there is lifting of a mass. So, that is essentially what we would like to have. So, in this kind of a process, if I remove any of these blocks, little tiny blocks, so before I removed the block, this system was in equilibrium because the pressure below is balanced by this mass plus atmospheric pressure above, and the piston is stationary. It is a frictionless system. If there was any imbalance in force, this piston would move, but right now it is in balance and it is in equilibrium. So, if I remove one tiny block from this, the equilibrium is slightly disturbed, but we are never far away from equilibrium. We are still close to equilibrium, but we are not quite at equilibrium. There is some small imbalance of forces and the piston moves slightly to come back to equilibrium. Then if I remove one more small block, the same process happens, the piston moves slightly again and we are back to equilibrium. So, what we see is in this kind of a process, we are never far away from equilibrium. The forces are never far away from being balanced. They are slightly imbalanced, but they come back to balance. So, there is always resistance to the movement of this piston. So, it is not like in the first case where we removed all of the blocks at once and the piston suddenly jumped away and ran very fast. So, it is moving very slowly. So, there is resistance to the movement of the piston because we are very close to equilibrium, not because of friction of any other thing of that kind. So, this kind of a process is what we call as a quasi-static process. It is almost static. The piston is almost not moving, but it is moving slowly. So, this would be what we call as a fully resisted process or a quasi-static process. And in this kind of process, the nice thing is that because it is always in equilibrium, we can measure properties of this system. We discussed in the first lecture, when we looked at properties, we said that we can only measure them when things are at equilibrium, because we said, for example, if the piston is moving fast, then the pressure at the top and the pressure at the bottom may not be the same thing. And then if I measure the pressure here and here, I get different values. I do not know which represents the pressure of this system. But if this piston is moving really slowly, then the pressure at these 2 points would be the same, and it will also be the same at any 2 other points. I can use any of them to represent the pressure. So, I know the pressure of the system. It is moving slowly. I know the volume of the system at any point of time because I can see it. So, this kind of a system would be a quasi-static process which the system is undergoing. We would also call it a near equilibrium process or a fully resisted process, and I can measure all the properties here and I can calculate the work which is done in this case.